In our previous video exploring maxon datasheets, Gaz had highlighted upon the thermal data information relating to maxon motors. As promised, we will discuss a little deeper into the thermal perspective of maxon motors. I'm Ronak Samani, technical engineer here at Maxon UK and Ireland, and in this video, I'll elaborate a little bit further on those thermal parameters and explain the thermal behaviour of maxon motors. Before I do dwell a little further to thermal behaviour, it's important to note why motors heat up and where this heat is generated from. I've described before that motors transform electrical energy to mechanical energy, but in order to do so, there needs to be power provided to the system. In a motor, at the input side, the electrical power is defined by a product of the voltage and current, and on the output end, the mechanical power is defined by a product of torque and speed. In an ideal world, engineers would like all the power to flow from the electrical domain through to the mechanical, thus utilising all the power available at the input. However, in reality, this isn't the case, and power is lost to other forms. This may be due to the friction from bearing elements and brush elements, but this is often neglected. Of more importance is the losses due to the winding, and sometimes known as copper losses, but at Maxon we define this as joule power losses. The joule power losses can be determined from Ohm's law. Substituting Ohm's law into the electrical input equation, we can see the dependencies, the joule power losses. Observe the equation. There is a direct proportional relationship to the electrical resistance. However, a much more profound effect comes from the current. As can be seen, it's to the current squared. That means at twice the current, the power losses are 4 times more. So now you know why motors heat up, that not all the power can be utilised, and where this heat comes from, the sources being the current and the electrical resistance. But how exactly is the heat transferred? Well, this is best described by thermodynamics, that heat always transfers from hot to cold. There must be a temperature difference. The general process of heat transfer in motors initiates at the winding. It then elevates to the stator housing and finally finishes at the ambient environment. This is best described in the diagram. Following the red line, the joule power losses in the motor winding heats up the coils and increases the temperature. This temperature rise is of importance to engineers as it relates to line 22 of Maxon motor datasheets, the maximum winding temperature. At this temperature, the motor is subject to its maximum continuous torque and hence its maximum continuous current. The temperature increase in the winding is governed by the following equation. As you can see, a proportional relationship exists with the joule power losses in the winding. But there are other 2 variables introduced. What are these? Let's look further. Simultaneously, as the winding temperature increases, the heat is then dissipated to the stator housing. This is shown by the grey line. Finally, the heat then dissipates to the ambient environment. The 2 variables that I had introduced relate to the thermal resistances and govern how well the heat is dissipated from the surfaces. RTH1 denotes as the thermal resistance between the winding and the housing. RTH2 denotes as the thermal resistance between the stator and the ambient. The thermal resistances are listed and quantified on line 17 and line 18 in Maxon motor datasheets. RTH1 is a parameter that is purely dependent on the design of the Maxon motor. Therefore, as a user, there is not much control for this. However, RTH2, the thermal resistance between the stator and the housing, is a parameter that is of control to the user. Enforcing some external cooling to the surfaces will help in better heat dissipation. The goal is to optimize either of these parameters such that the winding temperature is kept to a minimum and allows better motor operation. The last parameters that I'd like to explore is the thermal time constant of the winding and the thermal time constant of the motor, listed and quantified in line 19 and line 20 of Maxon motor datasheets. For motors that are in continuous operation, at some point the temperature difference will stabilize, and eventually a thermal equilibrium state will be achieved. The graph presented illustrates the exponential rise of a heating and cooling of a simple body. It's at this point in the curve that denotes to 63% of the steady state condition and takes approximately 1 thermal time constant to do so. At approximately 4 to 5 thermal time constant, the final steady state condition is achieved. And there you have it. So now you know why motors heat up, where this heat is generated from, and how exactly the heat transfer process takes place. It's important to bear in mind though that this thermal analysis does have its limitations, and certain calculations presented will only be approximations of the overall model. The thermal analysis that I presented is subject to a few underlying assumptions, such as the heat transfer is assumed to be uniform over the body elements, and that the heat transfer is proportional to the temperature difference. A vital point that I'd also like to make is that this thermal analysis is only valid for continuous operation. If the motor is to be utilized otherwise, then a new thermal analysis approach will be necessary. In our next video, Gaz will cover thermal operation of DC motors. As always, thank you very much for listening, and if you require any further information regarding thermal reaction of maxon DC motors, then please contact us using the following details.